So my name is Steven, and I'm here to talk a little bit about hardware stuff, which is a big departure for me from the norm. I'm traditionally like a software guy. Last year, I was at REcon talking about software sandboxes. I did a talk called Escaping the Sandbox, where I talked about how to get inside of sandboxes, kind of how they worked, kind of what the state of the art is, and hardware stuff. Before I dive into the presentation, a little bit about me. I run a blog called Don't Stuff Beans Up Your Nose with a guy back there named Steve. He's just waved, he has a ponytail, you can beat him up later. So I used to work at Montesano and worked at McAfee, and prior to that, a defense contractor. So I do vulnerability research, reverse engineering, and that kind of stuff. So that's me. So this talk outline, the talk is basically about hardware stuff. And hardware stuff has been something I've always kind of flirted with. I'm not an EE guy at all. I'm barely good at software, so hardware was really difficult, or there was a huge barrier to entry for me. So I'd always thought about it and romanticized it. Years ago, I bought the Wiggler after I saw Barnaby Jack's talk at Black Hat about JTAG and stuff, and I was going to get into that, and it just never happened. I used to get Nuts and Volts, if you guys ever remember that magazine, Nuts and Volts. And I used to buy the PIC development kits, and I never wrote anything with them. They just sat on the shelf. So maybe about 6 to 8 months ago, I went independent and I had a lot more free time on my hands. So I started diving into some of this hardware stuff. And so this talk is kind of about a lot of the stuff that I've learned over the last few months, which isn't very much. Everything I know, I'm basically going to tell you in this talk. And some of the hardware things that I learned over the years that were helpful. So like building Ethernet taps, building some serial taps, and things like that for some hardware projects you might run into. So this talk was originally given at SummerCon too, so the style may be a little more relaxed than you're probably used to. So I apologize for that ahead of time, but hopefully you'll still pull something from it. So basically the talk, what I'm going to talk about today is, I was really surprised when I started looking at hardware to find out how many standards there were, so to speak, down on the PCBs. I was really surprised to see that what I thought was a high barrier to entry was actually pretty low. A lot of these chips use protocols that we're familiar with kind of from our normal computer usage, so serial protocols. I was really surprised to find that little EEPROM chips sitting on boards could actually speak serial protocols. So that was a huge discovery for me, and this is kind of a talk about those different protocols. So I'll talk about this stuff just a bit, and then I will show you some of the real-world applications that I was able to apply to find out cool stuff. There will be some demos. I have maybe 8 or 9 embedded videos that'll show you some of my hardware rigs and some of the stuff that I found. And I'll end it out with a really cool cable modem bug. It's just a big bug and a very common cable modem. So yeah, this whole thing started with low-level communications. I didn't do that. Oh, you did that. Oh, are you Jonas or wait, what's your name? Yeah, I follow your blog. Oh, that's awesome. See, REcon's great. Yeah, so I follow your blog. You do great. I love your photography too because I'm into photography. Cool. So we'll talk later. So my question was this whole thing started how do low-level things interact and communicate? So like I said, I was really surprised to find that there are actual standard protocols down there, and the ones that I really honed in on for this talk are the serial protocols. So I was surprised to find that you're familiar with RS-232, back when you used your WIN modems or whatever. You were connecting a 25-pin serial into your computer, and then maybe if you're really old school, issuing AT-style commands and stuff to talk to BBSs, or you're just using AOL to get on AOL or whatever. So there turns out that there's a lot of other serial protocols down there also. And the ones I discovered were I2C, SPI, and microwire. And specifically those two, SPI and I2C, tended to be the ones that I ran into the most in different hardware things. So it turns out that I2C and SPI are extremely ubiquitous. They're used everywhere. And I'll go through some slides to show you exactly where I started to find this stuff. But after a while, like when I built my sniffing rigs and stuff, and I was like, all right, let me try to see what this looks like on the wire. I would like order accelerometers and stuff, and all these things use I2C and SPI. So I was ordering all kinds of little crazy little ICs and chips off of SparkFun and like DigiKey and stuff, and just sniffing the hell out of them. So everything uses this stuff. So these are the four major serial protocols down there. So there's RS-232, I2C, SPI, and microwire. And like I said, I2C and SPI are the most common, but there's, and these are just kind of a comparison chart. It basically works out that I2C is the one that's used the most because it's the simplest. It's the easiest to implement in hardware. And the reason for that is because most of these other serial protocols like have support for having multiple controllers, or sorry, multiple masters on the bus, and they kind of have, like the spec is a little more flushed out. With I2C, it's just a single master-slave bus, so there's only one master on the bus at any given time, and just the basic messaging is very simple. So yeah, Occam's razor. So I2C and SPI, the simplest ones, they win. So they tend to be implemented in the most controllers and the most chips and stuff like that. So, so the one that I wanted to take a look at first was I2C. I2C is basically like it helps to think of it as building small local area networks on a PCB. So you can have an accelerometer, you can have EEPROM, you can have another controller talking to another controller, and all of these things can be interlinked with a very simple serial protocol. You can have one controller querying the accelerometer, you can have the single controller writing values from the accelerometer to EEPROM, all via I2C. It's got different baud rates and stuff. We don't really care about too much of that. What we really wanted to do was start to take a look at it and tear it apart. So not being an EE guy, I kind of approached this in a very, like with child goggles, basically. I was like, what does this stuff actually look like? A lot of this stuff was kind of scary to me, these like weird little rectangle things on a line, these knots on a rope thing. I didn't really get it. But after a while, it started to kind of make sense, and you can see here that it's pretty simple. Like whenever the line is high, forgive me if I'm insulting anyone in the room with this very childish description, but whenever there's whenever the line is high, then you know that there's a voltage on the line. Whenever it's low, you know that it's not, and that's basically ones and zeros. So basically, you have this clock pin that's constantly setting. It's like, think of it as a metronome. And that metronome is kind of the beat that the data pin plays to. So this clock pin sets the metronome, and then the data transmits to that metronome. So the data and clock pin are always going to be together, and they form the basis of the I2C protocol, the two-wire protocol. So, so with those basic fundamentals in mind, I was like, all right, let's go try to start sniffing. A few things to keep in mind is the basic patterns for how I2C is kind of brought, like when you watch an I2C pattern, there's going to be a specific place that marks where the data begins and where the data ends. And I'll come back to this slide a little bit later when we actually start looking at dumps. But before, I promised you, I tell you like what uses I2C, and basically it's everything. So I found this stuff in batteries, analog to digital converters, temperature sensors, I told you accelerometers. And because it's using all these small little ICs and PCBs, you find them in larger consumer electronics, especially people who OEM like accelerometers from one specific vendor. So you can find these things, I mean, I'll show you some slides. Well, here, let's just dive right into them. Like the NUC, for instance. The NUC has SPI. Underneath the micro SD slot, there is a serial port that allows you to console into the box and receive debug information. This guy, I found this video on YouTube, and you can see it's super popular with 16 views, but but this guy was basically just showing off his new, whatever, $5,000, $10,000 oscilloscope, and the way he was showing it off was by connecting it to the clock and data pins of an I2C chip that happened to be inside of one of those glucose meters for diabetics. So he was basically just doing the fundamentals of what I'm going to show you later, just to show off his oscilloscope. So there you go. I2C is inside of medical equipment. This guy, I found this on, this was like a link off of a Hackaday link a long time ago. This guy had one of those old school like video capture cards. It was like one of those Windows the TV receivers for Windows. And the company originally released the hardware for Windows, so like they had one group of developers who had this like really elaborate and really like well spec'd out application and kernel module and stuff, or driver or whatever. And then they wanted to support Linux, and the Linux was kind of an afterthought. They hired like, you know, the second-rate developers, and it turned out there were a lot of implementation differences. And this guy was really fed up that his Linux box wasn't working as well as his Windows box with this hardware. So what he did was he set up a small I2C sniffing rig and sniffed commands going across, I think being read from EEPROM or going across an I2C bus. And he did that for basic actions inside the UI in Windows, captured all the traffic. Then he did the same thing and sniffed all the commands from Linux and realized that there were actually command and implementation differences. And then he just rewrote and patched the driver and got it working. So this is a really cool example of how I2C sniffing is actually usable. I also found lots of I2C in these OEM chips, like these like companies like Fujitsu will like mass produce like a system on a chip for appliances. And this is a microcontroller for use in home appliances like refrigerators. Pretty much every new home appliance is using one of a handful of microcontrollers, and this is one of them. So Fujitsu makes a single board computer that has like you know, controllers for sensors and thermometers and all that kinds of stuff, and it's programmable and debuggable and interfaceable using I2C and SPI. This is another cool thing. A guy had an old school pinball machine, and it turns out that some of the EEPROM was I2C EEPROM. So yeah. And then this is kind of a peek at some upcoming stuff this summer. Charlie Miller is doing a presentation this year at Black Hat, which I have helped him out on a little bit, that used I2C sniffing to interface with the batteries on MacBooks. So it turns out that in every MacBook Pro, there is a battery that has an embedded I2C controller. So. Also, other stupider stuff like Wii's have I2C, so the Wii Nunchuck uses I2C. And this is like, I don't know, some maker people like to use these things for projects, and some guy made a propeller, nunchuck, Arduino wheel thing. So, yeah. So it's everywhere. And it's also the basis for SMBus. So if you probably poked around on your, I don't know, Lenovo or IBM box, or like even on your Mac, you see there's something called SMBus, which was like Intel tried to design this standard for kind of like hardware health querying. So you can do things like ask the battery how much charge it has and all these other kind of hardware diagnostics. It's like a standard for hardware diagnostics for PCs. And that's all implemented over I2C. So that's all well and good, but the question is, like, how did I actually begin to find this useful? So I founded I2C and SPI in a lot of embedded projects. So the two examples that I'm going to show you are the cable modem. I've also found it in other routers. And then one of the more interesting and more ubiquitous places I2C exists is in VGA. So on every VGA cable, there are two pins that are used to communicate between the controller and a display, and those speak I2C. So when you plug in your monitor and you wonder how your computer magically knew that you got that brand new Dell monitor, it's because over I2C, your controller is saying, hey, what kind of monitor are you? And then responding over I2C is your monitor saying, this is my vendor ID, and here's this big blob of data that represents what I can do, like which resolutions I can do and which refresh rates and stuff. So that was really interesting, and then also found out that HDMI uses this as well. And we all know HDMI has a whole layer of protection mechanisms for like Blu-ray and stuff called HDCP or HDCMP, which is like, there's a whole key exchange that happens over I2C, so that you can't basically sniff the video connection and like rip DVDs. So that all happens over I2C. And then the last really cool implementation is EEPROM. I found out there's lots of I2C EEPROM in devices. So this is kind of all the hardware that I just picked up over the last couple months to help me out with this stuff. I started out with a Bus Pirate, and Bus Pirate's like this Hackaday project, if you guys follow Hackaday at all, that is, it's kind of like a Swiss Army knife. And it turned out that this was really great because it got me excited and got me actually talking to stuff. But as I actually started trying to use it, it's really crappy, basically. Like it starts off well because it's 20 bucks, but then you realize that, so like basically it allows you to terminal into it using PuTTY right on the COM port. But then when you start doing things like sniffing data, the data that it sniffs, it just dumps back to you in ASCII form. So you have to write something else to convert like the literal 4-character 0x90 to that actual byte representation. So like a lot of that stuff started to make me angry. There's no binary interface. Travis Goodspeed, who's here, has the GoodFet, which is kind of his response to the crappiness of the Bus Pirate. But you have to assemble it. So Travis, yeah, I'm not good at soldering anything. So I found a bunch of other stuff to use. I used the Soleil logic analyzer, the Beagle, and I'm going to go through all these and show you what they did. And I even got an oscilloscope. I was intimidated by these things for years. I only used them like once in a physics class in 11th grade, and that was about it. So I actually got to use an oscilloscope, and I'll show you some demos of how I use that. So yeah, the Bus Pirate is really cool to ramp you up. So if you want to just get immediately started and you knew nothing about this stuff, like I knew nothing, it's a really great place to start. It's got some Python libraries, C libraries. You can use PuTTY and terminal right into it. It's really nice, and it interfaces with a whole bunch of stuff. I'm not going to steal that from them. They really made this thing talk to everything. One wire, it does I2C, it does SPI, it does raw 2-wire, MIDI, it does a lot of stuff. And it's all accessible through this cool iOS style menu when you console into it. So here's how it looks basically. You just, I use Device Manager, you find out what virtual COM port it puts itself on, and then you connect to that COM port using PuTTY, and it drops you into these little cool CLIs. And then you can like interface with different pins and do lots of cool stuff. So then basically after I started getting annoyed at the Bus Pirate, and also for different functionality, I kind of discovered what the use of a logic analyzer was during all this. I picked up something called the Soleil logic analyzer. And this thing, for laymen, basically is a godsend. So you just plug this thing into your computer. It's got this handy little interface that literally maps these colored pins, or sorry, those colored wires, to actual colors in the UI. So whatever you connect those pins to will be represented as a square wave inside of the UI. So it's dead simple. You just literally clip it onto something you want to monitor, and boom, you got output. So the really nice thing about Soleil also is that it has these analyzers, which are kind of like Wireshark, what are they called? What are they? Thank you, dissectors. They're kind of like dissectors, but it does it for specific things like SPI, I2C. And then it'll convert that data for you, and then it'll actually dump it out in CSV or raw binary. And this was kind of what I used to begin some of my hardware projects. I'll show you this stuff. So the Soleil will work very well for capturing data, but then if you actually want to do some real hardcore like bus sniffing, I got this thing called the Total Phase Beagle, which has a really, really nice interface. It's got kind of like a Wireshark style real-time traffic graph or whatever you want. And then it gives you, when you select the individual packet, it'll give it to you in like the traditional offset, hex, and ASCII representation. It's really nice. So I highly recommend this for I2C, SPI, and all kinds of sniffing. They have a bunch of different models. I got the lower end one, which is just SPI and I2C, but they have like a full speed USB 2.0 analyzer also, where you can just use this thing to sniff USB. And then lastly, Arduinos. So like I've been hearing a lot about these stupid Arduino things from like lamers at maker fairs and stuff, like guys who make LEDs blink and Christmas lights do stuff. Like I'd always heard about that, but I was not really excited by it at all. But one really useful thing I found is that Arduinos speak I2C and SPI. So you can write these really simple C-like programs inside of this ugly Java interface that they compile down to some proprietary crappy AVR code, and then they load it onto this Arduino, and then it executes and gives you access to the pins. So as a layman, that was great. Like I already know C, it's easy to read, and I can just quickly get my stuff to interface with the I2C and SPI pins. And then lastly, I got this oscilloscope. Like back when I first heard about oscilloscopes, they were prohibitively expensive. Like they were, the old tube ones, and they were like, they cost as much as a car. But now there's a lot of these quote-unquote toy oscilloscopes, which are useful for basic projects. And this one was only like $89. It's called the DSO Nano. So I picked up one of those. Didn't think I'd actually have a use for it, and it turned out I actually did. So I'll show you. But before we go into using that actual hardware, I'm going to kind of digress a bit and show you some of the other stupid hardware tricks that came useful over the last couple years, especially when I was a consultant. First one was a passive Ethernet tap. So it turned out we had this black box that we were auditing, and this thing spoke Ethernet sometimes, and it spoke something else some other times, and we couldn't figure out what it was, and it was kind of just a see what you can find kind of thing. And we just built this lame passive Ethernet tap to kind of sit between the two, and the reason why it's passive is because there's no logic in there. All the pieces for this I literally bought from Home Depot for under 20 bucks. And it basically splits the transmit and receive pins onto two separate ports, and then you can set two machines there and just listen to the conversation. So that was really cool, and we actually got some neat stuff with that. So here are the two machines. The proof of concept here is that I have the left laptop talking to the router through the passive tap, and then the other machine is just sniffing with Wireshark. So pretty lame stuff, but it's actually really useful to have these little tricks in your bag. This one is a little bit cooler. This was one of my first projects as a consultant. I was sent out for a 1.5 month engagement, and they literally just dropped me into a company that had a black box that was deployed in the field. So these things would be up on power poles, these things would be hidden in sewers, and they had all kinds of like telemetry stuff inside of them. And I was in over my head. I was like, this is my first project. It's like my first week at the job, and I knew I was gonna get fired. I was like, there's no way I'm gonna succeed on this project. So like after the first 2 days of peeing on myself and panicking, I bought some new pants, and then settled myself, found my aura, and then sat down and popped open the box in one of their labs. And it turned out that it had all this proprietary stuff in there. There's like this proprietary motherboard or whatever, and it had all these crazy daughter boards, but there were 2 GPRS modems sitting in there. And the main board communicated with the GPRS modems via a very recognizable 9-pin serial cable. So it's like, oh, that's kind of cool. Let's waste the next week trying to figure out how I'm going to fail at this. So I went on the internet and found some diagrams for building a serial cable. And because the diagrams are pretty simple, you have your transmit pin, you have your receive pin. Say, hey, why don't we try splicing those pins off into a separate adapter and see if I can sniff the data between the two. And so I spent about a day and a half learning how to solder and making it work, and I hot glued it all together and came up with this monstrosity, which basically gave me half duplex access to the data. So even though I only had one adapter, I had to put the adapter on one way and I got all the transmit data. If I flipped it the other way, I got all the receive data. But it turned out that this thing, the main board, was actually reporting all of its telemetry data back to a home office via the GPRS modems. And it was doing it without even doing like PPPD or anything. It would literally just ATDT dial up this thing, a modem would pick up, and it would just transmit a blob of data. And I was like, okay, so I spent a little while working at that. They had some CRCs in there that I had to figure out. But after all that was said and done, we had SQL injection into their backend, right, with a serial cable. So you guys weren't even there, so why are you clapping? Anyway, no, but thank you. So yeah, this was a really cool trick, and so I just threw it in here, It's a, here's a diagram for a tap if you want to build one, so that's kind of cool. So getting back to the hardware stuff, building your lab. I gave you the whole list of all the cool hardware, and then, so basically, what do we want to do? We want to sniff data on these different pins, right? So my test environment was, I was like, all right, so in a perfect environment, how would I begin sniffing I2C? So my first idea was, let's get two Arduinos talking over I2C. And I got that working. And then I emailed Travis Goodspeed. I was like, hey, do you know of any like ICs I could use? And he gave me a list, and he's like, get some I2C EEPROM. And then sure enough, I found a vendor of I2C EEPROM, ordered a bunch of those, and then just got my Arduinos talking back and forth to the EEPROM, just writing values to memory, pulling them back out, writing them to memory, pulling them back out. And then once I got that set up, then I have a perfect control environment for setting up my tools to sniff, and then I can kind of learn how, you know, the oscilloscope looks when it's attached to those data pins and stuff like that. So Travis, I also follow your blog, and this is a blog post you did a while back. So this is kind of a digression, but eventually we're going to be attaching to pins, and I thought this was a cool blog post he had on clever ways to attach to pins that are kind of buried or very hard to get at. He uses a hypodermic syringe. So you use the sharp tip of the hypodermic syringe to make contact, and then you actually can clip your trode sets around that. And I thought that was a really clever way of getting to pins. There's other cases. I worked on a project where we were looking at USB sticks, and this is one of the USB sticks we ran into. It's actually covered with this anti-reverse engineering epoxy, which is basically just goo that dries, and it prevents you from touching pins. But it turns out you can defeat this stuff also. I didn't do this, but it turns out that there's all these crazy people on Usenet that make acid baths and stuff. So, and then there's like YouTube videos. You can defeat some of the simpler epoxies with a heat gun, actually. If you just point a heat gun at it, you can flake off the epoxy. All right, so back to the to building the lab environment. So the basic thing is once I got my, my devices talking to EEPROM, or I got my two Arduinos talking, the technique is dead simple. And I'm writing this to you as if I was writing to myself 6 months ago. Keep it simple. Basically, all we're going to do is, firstly, we're going to have a question about some pins we see. All right, what do those pins do? So we just attach, the first thing we want to do is attach our voltmeter, make sure it's not some crazy voltage that's going to burn out our equipment. And if it's something simple, like 3.3 or 5 volts, then we know, hey, okay, there's something there that we might want to investigate. And then my next technique is, without knowing what those pins are, we don't know that, we don't know there's going to be I2C or SPI there. So what do? What I did is I attached the oscilloscope. And I used the oscilloscope to identify a square wave pattern. And the square wave is basically what kind of tells you that there's data actually being transmitted, because if it's an analog pin, you're going to get like an actual kind of curve, right? But if it's data, you're going to have transmit, and you're going to have it drop off, transmit, drop off, transmit, and that forms a square wave. So that tells us that there might be data there. And then after that, we connect the logic analyzer, and that gives us a little bit more information. And then if you're able to identify that as like a data stream that might be SPI or I2C by running some analyzers, you can then plug in your specialized equipment like the Beagle. So first things first, I used the Arduinos and connected them to EEPROM. This is just stupid code from the sketch that just writes to the EEPROM and reads from the EEPROM. And this is a video. So it's not playing over here. So basically, this is the rig. Ignore some of the other stuff. I'll get to that later. But those are the two Arduinos. That Arduino is connected to the main PC via that stupid USB hub to that machine. And so what I'm doing here is I'm using the oscilloscope. So those are values being read from the EEPROM. And you can see it flashes down there, so it's like reading the string, printing it, reading the string, printing it. And then simultaneously, we're identifying the square wave pattern as the data is being read from EEPROM. So if this was the real world, I'd have my oscilloscope attached, and I'd be seeing, oh, there's a square wave there. There's probably data being sucked off that pin that I'm watching hit the oscilloscope. So that's the first technique. So then now that we identify that there's actually data on those pins, that's the EEPROM. And the solderless breadboard, that's really dark. Sorry for that. So that EEPROM is then connected to the Arduino, and we're just doing the same thing. reading values out of there. And then instead of using the oscilloscope now, we're using the Soleil interface. So we're just going to, my SLR does not autofocus in video mode, so forgive the focus. So yeah, so we have all those individual pins. Those pins are connected. And then we see that there's the regular square wave, so that's probably our clock pin. If we didn't know what that was, we can probably deduce that that's the clock pin. And then I click capture, and it captures data. And you keep zooming in. Boom, then we have like a conversation. Oh, let's zoom in. The interface for the Soleil is really slick. You can just like select a small area, zoom all the way in on it, and then the closer you get, it just gives you straight byte values. It's like straight up for lamers like me. It's great. Look at that. So that's the Soleil to capture I2C data from the EEPROM. And then lastly, we use the Beagle. So we plug in our really super secret weapon, and what it gives us is you see all the transactions, you see the read events and the write events. And the way that it works is that you, for EEPROM, you tell it which values you want to read from, and then it returns to you the value that's at that location. So you always get a write, and then you get a value coming back. And in this case, in the small hex value, you see I have that single packet selected, hex value 68, which is ASCII H. That H is the this is the H from the this string. So that's us capturing that single byte as it flew across the wire. So now that we have this like cool control environment built, now let's actually take a look at real world stuff. So I wanted to set this loose on VGA, and without going into crazy detail, basically I told you when you connect your monitor to your controller, there's a small communication that happens, and they're actually expanding. So like the basic conversation is just question response. But then they have these like expanded extensions that are used by a lot of appliances. A lot of people are embedding control channels like volume up and volume down, where you can actually tell your monitor that you want to increase or decrease the volume or change the contrast. All that stuff happens over I2C. But the basics of that conversation is in a specification called DDC, which is data display channel. And then the extended data display information channel is the one that I told you has the extensions and is used for control and stuff like that. So, so what we're going to do is try to capture that data. We want to see what is actually happening. So first things first, you find your VGA pinout specifications, and sure enough, boom, pin 12 and pin 15 are the data and clock pin for I2C. So I don't know what I'm doing. Again, this was all new stuff to me, so I went really ghetto styles on this. So basically what I did was I built a simple rig that was, the heart of the rig is a breakout, a VGA breakout thing I bought from this company called Gravitech for like $5 each. And they had this little extension that allowed you to slot it into a solderless breadboard. And because I don't know how to solder to save my life, so I was just using jumpers and stuff for this whole thing. And then I basically connected all the pins, and this is my first test to make sure that my pinouts actually work. The fact that we have video is a good enough testimonial, but then just to make sure everything works, I said, okay, since VGA is analog, let's pull the red pin. It turns out that red pin's pin number 1. So theoretically, if I pull red pin number 1, then the color is going to disappear, and then I know the rig works, right? And this is just demonstrating to you that the video is actually flowing through the rig. So it's a little slow. I grab pin number 1. What if that hand was white? Would you think I was like lying? So I just pull the pin 1, and then sure enough, you can see the color flicker. The red color disappears. So you know that video is definitely flowing through the rig. So now that that's all working, we set up the actual tap to capture the data. So for this, because I have those jumpers, I can just pull 2 of the pins off for pin 12 and pin 15 and run it right into the Soleil. So that's exactly what I did. That's the rig again. Going up into that display. So really, when I first started doing these tests, I was just plugging it in, allowing the controller to talk to the monitor. But it turns out that Macs have this really neat button inside of display preferences called detect monitors. And what that actually does is tell the VGA driver to write those values to the I2C pins to request that data display blob, that DDC blob from the monitor. So I could just, instead of, if I was on a Windows box, I'd probably have to keep plugging it in. But on this Mac, I could just sit there and press the button, and I knew that data was going to be on the I2C pins. So I don't really know what's going on in this video, honestly. I lost where I was. We can skip to the next one. I'll actually capture this data with the Soleil now. So Soleil is plugged into the rig, and we're going to plug the monitor in. We got our pins all labeled inside the UI. We start capturing. The hand plugs it in. See the display. And then sure enough, on those two pins, we were able to capture some data across the I2C pins. So we'll zoom in and take a look at that. Now the Soleil has the option to dump this in binary form or like the CSV file format, but we can just import this or do the same thing with the Beagle, and it'll give us a better representation of that data. So this is basically the conversation. The regular high-low is definitely the clock pin, and then the other pin is definitely data. So when we actually connect this to the Beagle, we see in a better representation what this blob looks like. So sure enough, I was plugging this into a Dell monitor, and down there on the bottom, we have you can see the Dell vendor string. So then the next step for me, this HDMI also uses this, but I kind of skipped HDMI and wanted to move to the next step, which was maybe I can start to fuzz. Like maybe I can actually start talking to controllers from an Arduino or from some kind of controller and see what happens. So basically what I did was I built a very simple fake display, which was basically an Arduino that received the I2C commands and responded. And honestly, I didn't find anything too interesting except for a few kernel panics. But I don't know if that was because I was mucking around with the SM bus primarily. But this is definitely a right place for people to look. Like there are appliances that use this stuff. I haven't even looked at EDID at all. There are a lot of people who are hiding control channels across VGA and HDMI ports. I was told that some of the earlier versions of the CR48, which is that Google thing, in developer mode had a terminal on the HDMI port or something. I don't know. These are all really cool places to look, and you could use rigs like this to find all this kind of stuff. So a real application for like a real project was embedded systems, like actual vulnerability research. And one specific target is and a public target is one that we looked at on the side, which was a specific cable modem. It turns out this is one of the cable modems that runs its own little web server. So like when you do things like request a bad DNS, it'll kind of redirect you internally. And there are other times where it can be remotely like turned on for help menus and things like that. So the remote, I don't know, Time Warner can turn on your cable modem to give you assistance or redirect you to like a landing page and stuff. So that was really ripe. We're like, whoa, a cable modem that runs its own web server. But how do we start to interface with that? So it turns out when you look at the PCB, you get there are these 4 pins sticking up. And we wanted to find out what those pins were, and we got lucky in this case. So using that same technique, which I listed to you earlier, which is like connect your voltmeter, connect your oscilloscope, and then start connecting all your tools. We take a look at those 4 pins individually, and sure enough, we get a 3.3 volt pin. And Then we collect our oscilloscope because we want to actually see if there's data across those pins. My hunch was that there'd probably be data across those pins during boot or shutdown. So what I did was I connected the oscilloscope and just repeatedly pressed the reset button, and sure enough, we identified the square wave pattern on the oscilloscope. So then my ears perk up. I'm like, okay, that's cool. There's definitely data on those pins, or there's something happening on those pins. Let's take a closer look. And there it is again. You see that data blip across right as it reboots. So we connect our Soleil. So sure enough, I connect all of those 4 trodes to those 4 pins and begin capturing data. There's a really cool feature in the Soleil called AutoBaud, which will do its best to guess what the baud rate is, so you can get the right byte values. And yeah, so I used that a bit, and then captured the data. And here's me actually applying what's called an analyzer, which are basically the dissectors for that I2C data that was captured. And we got a bunch of byte values. So okay, what do we do with this? So I exported this to CSV. You can export it in binary form also, but I exported to CSV. And then a really simple Python script to import CSV and do some cleanup of carriage return new lines revealed logs of it booting. So you actually watch this thing start up, and it reveals information like it's running an ECOS real-time operating system. So then the next step is, all right, if we're getting all this cool debug information, let's start fuzzing this thing. And after a little bit of level 2 fuzzing, HTTP fuzzing, boom, right there on the SPI port. This bug was actually found by Raj, who works at Intrepidus Group. He was working with me on this project. So it's a really awesome bug, and it's exploitable. So yeah, wow, I'm really ending early, but that's the end of my presentation. And special thanks to Travis, who helped me out a lot over the last 4 or 5 months with questions and stuff like that. Guy Chris Shirk, who's like my EE guy, he tells me all the EE stuff. And Raj, who actually found that bug while fuzzing with our little rig attached. So that's it, hardware stuff for software people. That's all I have.